Today we've got Hamid from Parchem. From Fosrock. He's their forensic engineering specialist. He's well versed in all of the remedial works. His role there is the National Product and Specification Manager. And the idea there is so he can harness the high-performing technologies to respond to complex repairs and applications. He's got 24 years of experience in the industry. He first started with Fosrock International in Dubai, where he was for 14 years. He was able to see repair products in action on a vast range of projects in the Gulf, Middle East, Europe and Asia. He's got trusted expertise as demonstrated by his regular speaking roles at things like this. He's a good supporter of ACRA as well as other industry-specific seminars and presentations. He's also published numerous articles which you can Google or search to your heart's delight. He's a director on the board of the Australasian Concrete Repair and Remedial Building Association, that's ACRA, you all know that, and he's also a past president of ACRA. He's played an active role in HB 84, 2018, the amended version. That, of course, I hope you know, is a joint publication of ACRA, CSIRO and Australian standards. He's also helped produce and present many other remedial industry courses. Today he'll be touching on concrete structures mostly, how they should be managed and maintained to achieve their required operational service life. Existing concrete structures in Australasia can suffer from significant deterioration due to corrosion of reinforcement, which causes falling of the concrete and eventually threatens the structural integrity. In order to accomplish the durable repairs, it's imperative to examine the factors affecting the design and selection of repair systems, because they're an interwoven and composite system once they're installed. The precise specification of concrete repairs is one of the critical factors that dictate the success of that repair project, and success being it meets its required service life. Deterioration of concrete is complex matter, influenced by numerous physical, chemical, mechanical and environmental factors. That makes every concrete repair job a little bit different to the previous. Repairs are costly, time-consuming and disruptive, so ensure you get it right the first time without any severe side effects. Just a matter of process, if you've got questions, please put them in the Q&A and we'll deal with those at the end of the webinar, just as an efficient thing. If there's something red hot urgent, of course, pop your hand up and Nicole or I will help moderate that at the time. So I will now shush and hand over to Hamid. Thank you, Hamid.
Thanks, Graham, and welcome everyone. Good morning, good afternoon. Yes, still good morning. It's a very nice sunny morning in Sydney. I'm based in Sydney. So an excellent day. What a day. So my webinar is going to take around 40-45 minutes, and then we will have some Q&A session as well. So very rightly said, getting it right the first time in order to avoid any side effects. So the topic today is the side effects for concrete repair durability and compatibility and selection of materials. Studies in the field of repairs show that almost 50% of repaired concrete structures had failed in Europe and USA prematurely. This is alarming, and this is happening all over the world. So I just got these figures from a research paper, so I thought I should share. And we are talking here about the repaired areas. So what's the challenge? The challenge is, of course, the selection of an optimum repair material or material system, which is required for the success of any repair process. Of course, other factors are important, such as surface preparation and method of application and other construction practices. But to begin with is, of course, the selection of repair material is very important. Now, I'm not going to take you through today the EN 1504 holistic concrete repair approach. I think we have done a lot of seminars and webinars on EN 1504. The topic today is very well focused and targeted on very specific points so that we get enough time to cover those points. So this is a picture, a couple of photographs I'm sharing here. When I say compatibility or the failure, it's not only in repair mortars, but it could also occur in coatings. Either it could be due to poor surface preparation, but this one was because of compatibility issues. Probably in some other webinar, I'll go through in detail when we cover our coatings or other systems, but that was not a surface preparation thing. It was first the compatibility followed by the surface preparation. So as we know, and you must have seen the slide earlier as well, that concrete is subjected to various factors, external factors, corrosive agents, mechanical factors, atmospheric carbon dioxide. If you can see my cursor here, you can see soil, you have sulfate attack. In the red zone here, you can see it must be the splash zone or the cyclic up and down of water, tidal zones. That is one of the most aggressive environment in marine. So my point is that concrete is subjected to various factors and is always challenged by those factors. In buildings, we know that the facade, the external parts of the building, and same as with the bridge structures. If you can see the bridge hierarchy, all those elements and sub-elements of the bridge structure are subjected to environmental factors. As a result, if we have in new construction these type of problems, and none of these images are from Google, these are from various parts of the world where I have worked in the last 24 years. So we say that concrete must not separate. The cement paste, water and aggregate must be together. And if the aggregate and cement, they separate together, concrete paste separate together, this is segregation. If the water separates from the paste and the concrete, it's called slurry bleed or the bleeding. As a result, we end up having honeycombing. So these type of structures which are being designed for 70, 80, 90, 100 years, they need a repair mortar of similar properties, compatible to the substrate, compatible to the host concrete. So the question comes in the durability debate most of the times that do we need high performance concrete or do we need high performance concrete structures? So it's not only about the concrete that is being designed. We can design the concrete to the highest level, a double blend, triple blend. You add all those supplementary cementitious materials, microsilica, GGBS, fly ash, and all that stuff. But the most important thing is the delivery of the project, and during the operation stage, how the project and how the concrete was placed finally. And this is from Australia as well, this image. So this is not from Australia. These are from the Gulf states, I believe. So having said that, when we see these structures, these needs to be reinstated, repaired, rectified to their original strength. When we talk about concrete repairs, when we are repairing the structural element like columns and beams, that structural repair is a bit different than the concrete repair mortars which are used for protection or for just to fill the pinhole, for example, or blowholes, or just to protect the top surface against the ingress of chlorides or carbon dioxide. So it's very important to know that the repair mortars should be low in permeability, they should be compatible, and they should have long-term integrity. What do we mean by these three terms? When I say that in order to ensure the durability of repaired areas, the cementitious repair mortars must exhibit low permeability, low shrinkage, and compatibility with the substrate. So when we say compatibility, that means compatibility in terms of modulus of elasticity, thermal coefficient of expansion, and strengths. So most of the times we end up, we start from the strength and we end up here. So strength should not be the only criteria to select a repair or specify a repair mortar. We should also look at these factors for the compatibility. For low permeability, we should look at the repair mortars should have EN 153, what is this? The EN standard 12395 standard for the carbon dioxide diffusion resistance. Chloride as per ND build 443. So the repair mortars should comply to those standards as well. And obviously low permeability against moisture and water. And when we talk about long-term integrity of these repair mortars, that means they should have low shrinkage. And these shrinkage values are specified, sometimes what I've seen by different asset owners and engineers, based on the type of the structure and also based on the environment. For example, in marine environment, these values are more stringent. And same is with the chloride testing and chloride diffusion resistance as per NT Build 443. If they are non-marine, they are a bit lenient. If they are benign, they are a bit lenient. So it depends on the structure as well, but these factors must be considered. And same is with the bond strength. Very important to have a good bond strength for these repair mortars. This is a typical repair mortar specification. This is one of, so there are many others as well. So as I said, the carbonation resistance should qualify EN 13295 standard. The chloride diffusion test is very important. So these two testings parameter comes where, if I go back, they come under low permeability. So it's very important to understand when we say low permeability of repair mortars, that means they should be low in permeability against these corrosive agents. I call it corrosive agents. So it's not a normal cement, sand, masala mortar. It has to be, when we are talking of structural repair mortars, it's a serious business. That means we are trying to restore the structure to its original strength. And we are repairing, we might be repairing a structure that has a design life of 100 years. So how could we go wrong with not qualifying for the low permeability? And same is with bond strength, for example, and elastic modulus and so on. If I talk about shrinkage, which is the part of the long-term integrity here, the shrinkage of repair mortars, I was reading a research paper that says that it is one of the most important parameters during the selection of repair mortars. So I've seen that, repair mortar data sheets, sometimes they don't mention the drying shrinkage properties on the technical data sheets. I believe they should be mentioned clearly and loudly. So as you can see from this graph, as we go more than, this is in microstrain. So as we go more than 500 microstrain, the potential for the cracks increases tremendously. So the best is to have this as number of days from 0 to 28. So if you can fall in around at 300 microstrain is a typical value at 7 days, and 500 to 600 microstrain typical values for 28 days or 56 days. That is acceptable. But if we go like more than that here, you can see the higher the shrinkage microstrain values, the more potential for the cracking. So it's directly related to the drying shrinkage. So it's very important to have that property mentioned on the technical data sheet. The next thing is the bond strength, which is for the integrity of the repair mortar. So the repair mortar should have an excellent bond strength with the concrete. Now, just to make a point here, the bond strength that is mentioned normally as per the standards which are tested in the lab and mentioned in the technical data sheets, you can't achieve that at site most of the time. So there are specifications that outline what are the bond strength or adhesion, pull-off adhesion test requirements at sites. So there are acceptable limits for that. It could be 0.7, 0.8 or megapascal. Normally micro concrete, which is foam and pour, they can, and the sprayed mortars, they can go even 1 megapascal plus. And it can go even much higher than that, but this is as a thumb rule. The site bond strength is a bit different. So these are the different pull-off tests, basically for coatings, but we can consider the same thing if we are saying that if there is a failure between the primer and the repair mortar, it is called adhesive failure for primer and repair. If the failure is between the primer and the substrate, this is called adhesive failure between the primer and concrete. If the failure is within the primer, we call it's a cohesive failure. Is a failure is within the repair mortar. So I'm taking coating as mortar here because this is a repair webinar. It is called cohesive failure. If it's failure in the concrete, this is called failure in concrete, which is quite desirable for us, in order to have a good repair mortar. So in order to have good bond strength, obviously we need to have good surface preparation, exposing the rebar 20 to 25 behind and all that. So this comes in the operational part as well, but they are very much relevant to specifications as well. So specifications for concrete repair mortars are becoming increasingly comprehensive. It's not only we specify or the engineers are specifying the parameters, it's very important also to specify the operational part and the application part as well, which we do see most of the specifications comes out with these details. So durable repairs, if we need to have it, getting it right the first time and to avoid any side effects, what happens is that it's always better to add an anode as well at the perimeter, because I'm not sure if you've heard the concept of incipient anode effect. I'm sure you must have. That means that if you have repaired a certain area, you have removed the concrete, deteriorated concrete, this is the repaired area. After 6 months or 1 year, the adjacent area starts getting corroded. This is a side effect, by the way. This is called incipient anode effect, or the halo effect, or ring anode effect. And this is simply, it's a very simple concept that once the contaminated concrete is removed and we replace it with a new excellent repair mortar, what happened that we try to make that area as a zero chloride level. And if there are sufficient chloride ions, contaminated concrete in the areas which are adjacent to it, we will still have that electrochemical process starts, and we will shift the anode and cathode. So I didn't want to talk today more about anode and cathode, but I have some very simple slides to talk about it. So this is the area. Both the areas have chloride content more than the threshold value, which is 0.4% by weight of cement. This is 4%, this is 0.8%. Both of them are higher. However, the areas where you have cracks, you have higher chloride level. That means it has a higher potential as compared to the adjacent areas. So it will act as an anode, and the adjacent areas are still safe. In a cement matrix, they are cathode. So what happened? We removed that 4% chloride area and we made it 0 chloride %. So what happened now? The potential still exists. The difference between the two areas still exists. The only thing is what we have done, we have reversed the areas, as the repaired area is now called cathode and the area adjacent to it is now called anode. So this is known as, now what will happen, the corrosion process would start again and the areas adjacent to it would start deteriorating. So removing the chloride ions from the repair area reverses the potential difference, creating a new corrosion cell outside of that repaired area. We have done a great job, excellent surface preparation, very good saw cutting. We've gone beyond the steel rebar and all that stuff, but then it could still affect the adjacent areas. So the solution, which is most of the specifications are calling out for, is to add galvanic anodes at the perimeters so that to extend the boundaries of protection. So these anodes have radius of effectiveness and they can protect the areas and the adjacent areas as well. I have tried to show it in a small animation. Let's see if the technology works. Graham, I'll just play it, and just give me a thumbs up if you can see that. So this is how the corrosion process initiates. It's green still, but suddenly what happens, the aging factor, or it could be a concrete quality or cracks that have started the corrosion process. And as a result of that, we can see loss of section for the steel. But what was done is that we removed that contaminated concrete completely and repaired it with a good patching repair mortar. And what happened now, we have reversed the process, and the adjacent areas now that had lower chloride potential now have high chloride potential as compared to the repaired zone. And that has then caused that halo effect. So the solution is to have galvanic anodes at the perimeter, so that they not only protect the repaired area, but they also protect the incipient anode effect and the adjacent areas as well. And we could have extend the life of the structure for quite a number of years. The electrochemical process will still occur, but then it would occur in the zinc, which is surrounded by a highly alkaline mortar, galvanic anode, and that will not expand as the concrete and the steel expands. So it is keeping steel as cathode because we are introducing an external anode body. So this is also called a simplest form of cathodic protection, maybe galvanic protection. So so this was, as we are talking about side effects, so I just thought I'd mention it in the bond strength. Now coming back again to the bond strength, which is required for the integrity of the repair mortar. These are some of the projects that I was involved in, where the CP overlay was sprayed on. So again, it's very important to understand, to have a very good surface preparation as per the standard, as outlined in the standard. And so the surface preparation is important because these are spray applied. These are not traditional saw cut and repaired mortars. When we are talking of an overlay, the concrete substrate must be prepared to at least CSP 8 or 9 or similar. When we have a proper saw cut and a geometric pattern for sprayed mortars, they are already have a good profile. Let me see if it works. So there are sprayed mortars that can be used to be applied, and such surface preparation that you have seen in the previous slide would really provide a very good bond strength. So bond strength is not only about repair material. Let's have a look at this again, guys. So if you remember the initial slide that I've shown you, the bond strength falls under long-term integrity of repair mortars. So bond strength is not only about the property of the repair material, but it also depends a lot on the surface preparation. So as I said, it has two parts, and I'm touching more on the first part today about the repair mortar specifications, but I might talk about a bit on the other part as well. For the modulus of elasticity is also an important factor. For example, if you have a load-bearing column, if you see in the left-hand side, and there are problems and you repair it with a low modulus repair mortar, what's going to happen? It will not contribute in taking any stress loads. And all the stress and the loading would be taken by the damaged parent concrete that is of high modulus, and that at the end of the day would rupture or would not be able to withstand the loading. So when we are, I mean, columns and beams, these are load-bearing structures and elements, sorry. So they have to be reinstated with a proper structural grade repair mortar. Either it's a hand applied or a foam and pour microconcrete. All the properties other than compressive strength, the flexural strength, tensile strength, bond strength, all other properties are very important, and the shrinkage, drying shrinkage property as well. And obviously the modulus of elasticity is very important to have a similar. Probably I think it's for a 70 MPa repair mortar, the modulus of elasticity, or you call it tensile modulus or Young's modulus as well, or elastic modulus as well, is around 30 gigapascal, and for the concrete is also almost the same. So in EN 1504, the repair mortars have been classified as non-structural and structural. The non-structurals are R1 and R2, and the structural ones are R3 and R4. And they have, in EN 1504, they have outlined the minimum modulus of elasticity values as well. I think for R4 it's greater than 20 gigapascal. So these are the projects that I was involved in as well, in repairing the columns and reinstating the columns with a higher durability, a similar type of modulus of elasticity repair material. So it's very important while repairing such or reinstating such elements to propose us a repair mortar that has the similar modulus of elasticity in order to have a similar, so that they can take a similar type of a strain, you know. So yeah, the modulus of elasticity is a ratio of stress to strain. And as long they are similar, there'll be a linear graph between the two, and it works well, and they are fully, we call it fully compatible. So the purpose of showing this diagram here in the service life here is that normally the initial part where the corrosion stage just starts and propagate is the most vulnerable area where the interventions are required in terms of asset maintenance and asset management. Before that, we just do visual inspection and see how it goes. But the time comes when there have to be regular periodic maintenance. We have seen that the transport projects are very well managed, but in the building sector, I would say that we sometimes see globally, I'm not pointing here in Australia and New Zealand, but in globally what I've seen, there have been maintenance negligence during the propagation stage. So we should not be waiting till the failure or till the last stage where concrete pieces starts falling down, or where we call it delamination stage. So at this stage, these should be addressed and repaired with the correct material, so that if we repair at this stage, it should then extend to the desired service life. So we should not fall into a cycle of repairing the repair. It's all about doing it right the first time, selecting it right the first time, specifying it right the first time. So probably I show you the corrosion process here, another small animation that you see initially, in the initial years, no problem at all, but concrete would always be challenged to external factors, and you can see the corrosion, onset of corrosion after a certain number of years. Sometimes it could be much earlier as well. And suddenly it takes no time. When the chloride ions start attacking the passivity of the steel, or the passive layer of the steel, and the passive layer of the steel reinforcements is challenged, you can see the first cracking, first spalling, and structural failure. It is very quick, you know. So it's as I said, you know, at this stage, when the onset of corrosion, periodic maintenance must be done, and any crack or any, even if you see that there are cosmetic type of problems on the concrete, they must be repaired or protected with good quality repair mortars in order to avoid those external factors depassivating the steel. So we talked about the repair mortar specification. We talked about the long-term integrity, low permeability, and compatibility. These are very important parameters for any repair mortar. It's not the strength only. As I said, by specifying not only the strength, but also the low shrinkage, low permeability, and compatibility, we ensure that the repair mortars, that the repaired areas are durable, and the repairs are ensure for the durability of repair areas. When we are doing repairs, actually, obviously, surfaces should be saturated surface dry. We know that even if it's a fine, thin repair mortars, they should be SSD, saturated surface dry condition, and but there shouldn't be any free water, otherwise it will impair the bond at the interface. I've written an article on surface preparation that covers the operational part, I would say in quite a bit of detail, because it also mentions about the QA/QC at the end as well, about the testing for the bond strength. That was published in ACRA, in ACA magazines, and CIA magazines. So if you Google it, you might find it as well. But there is also a need of going back to basics. 20 to 25 millimeter behind the rebar. The standards also say that you have to keep on breaking the concrete until you reach the sound concrete. Sometimes it's not possible, and the concrete is very strong and very durable. There might be something going inside it. In that case, now the new innovations and technologies are in place. Those areas can be protected by a targeted approach, by adding galvanic anodes, by drilling it and inserting the galvanic anodes. This process is called corrosion control, where you have future potential for corrosion, and you want to protect and extend the life of a structure for, say, 30 years. So you're not then going to treat only a spalled area. The spalled area is there where the concrete is spalled. It's a stage 4, but it's the same structure. It might be the same car park. So you have repaired an area with the corrosion prevention, with the galvanic anode for a patch repair. But the areas which are in the same structure or a floor, it's very easy to do that condition assessment survey to see the chloride dust sampling, chloride profiles, and other carbonation testing. And then we can see that, hey guys, it's really important to protect that as well, because it's the same part of a structure. And the client or the asset owner is looking for the design and the service life to be extended to further so and so years. So definitely then you can do the, we are not going to break that whole area. So we're going to do the drill and hole and applying those corrosion control anodes as well. Hand placing materials are there. So this is a typical bridge girder picture, that where you have first layer of mortar, then you do the crisscross, you apply a curing agent, and then you apply a second layer. Now there are extra high build repair mortars available in market, where you don't have to really do so many sections in repairs, build up sections, I mean, and they can be built mostly in one section up to 80 millimeter or 100 millimeter in one go with an excellent bond strength. Similarly, after hand apply, there are sprayed on systems as well. For sprayed on, they are very fast in application, but this is also an important part in the selection for a durable repair, that if you have larger areas and if you have access to these structures where you can bring your machine in and spray is really good. However, we have seen sometimes foam and pour also work very well if you have an excess from the top bottom foam work underneath, and you can pour those if it's a slab. In such situations, sometimes if you can do a letterbox foam work and apply or pump as well. So there are different techniques, and it depends totally on the site allowance and whether this site allow us to take such equipments. So this is, I think let me see if it works here. Yeah. So this is a good surface preparation. These are excellent surface preparation. You can see excellent saw cut at the edges. So would definitely improve the bond strength. The sprayed mortars these days can go very high, up to 150 millimeter. This is dry spray mortar in one go, 150 millimeter. And vertical overhead maybe a bit lower, but sprayed on systems are really good repair mortars, and they're very durable as well. Excellent for larger areas. Micro concrete foam and pour it is very much similar to the micro concrete or self-consolidating concrete that is being used. And I think this started getting popular 20 years ago. And I've started seeing it's being used in different parts of the world, because this is polycarboxylate technology. And that is just like fluid, because it fills all the gaps. If this is your steel reinforcement, it will fill all the gaps around the steel reinforcement, giving no room for the corrosion to initiate. And that's why it's a bit, popular in critical structures or high design life structures. I think in Burj Khalifa, the tallest tower of the world, the self-compacting concrete was used throughout, right from the 2-meter dia piles, where I was involved, my company was involved as Fosroc, and it was extended then later on. I think it was also used in the superstructure then later on as well. So complete structure was casted by self-consolidating concrete. So these micro concrete is also, you can consider them as self-compacting or self-consolidating concrete, but the advantage of this is they comes into pre-bag, 20 kg bags, and you can mix it and pour it. So just imagine they are a typical structural grade repair mortars, and they are foam and pour application technique, and an excellent repair system for structural elements like columns and beams and retaining walls. I've written an article called Concrete Rectification Using Microconcrete Foam and Pour Technique. I think it was published again in ACRA, CIA, and Australasian Corrosion Association magazines. Have a read to that. It's a very interesting article. It tells a good story about these type of repair mortars. But just imagine if you have a gap of 500 millimeter, your hand applied mortar is not going to work there, because it's not easy to go beyond the rebars. And here we are talking of durable concrete repairs. We are not talking only a normal simple patching or with a masala mortar. It's a serious business, because we have to address the service life and the design service life of the structure that was originally designed. It is equally good to rectify defects in new construction, where you have honeycombing and some unavoidable circumstances could cause those even in new structures. And it's equally good for fill the gaps all around the rebar. And that's all from my side. I tried to be on time here, but just to summarize here again, that in specifications, compressive strength should not be the only criteria for the selection and specification of repair materials. Today, specifications for concrete repair mortars are becoming increasingly comprehensive. They should definitely cover all the necessary parameters to ensure the durability of repaired areas. I would say cementitious repair mortars must exhibit low shrinkage, low permeability, and good compatibility with the substrate. And the second part comes in the operational part and the application part. Thank you very much for your patience and for your investing your time this morning. And over to you, Graham, for any questions.
Yes, thanks, Hamid. Oh, okay. We've got one from Tahoodle Alam. What is the right process of survey and repair of underwater structures?
Okay, so Tawhid, if I pronounce it correctly, when we say underwater structures, that means marine structures. And in marine structures, one of the most harsh and I would say aggressive climatic conditions that normally appears in if you have your quay walls or if you have your piers at the splash zone, where you have continuous cyclic uh, um, rise and fall of your tides, that could really create massive corrosion cells in the concrete. So the best way, the topic today was not on covering on the condition assessment, but the best way of evaluating is, first of all, the visual, how it looks like. Is it really has passed the stage 3 and 4? We know the environment is already aggressive. We know it's high chloride, but still it's always good to have those chloride profiles. So once you get that chloride profiles, immediately we are able to understand, even if the concrete is intact and spalling is not much, but sometimes the chloride profile shows very high chloride levels. That means that they should be addressed accordingly. And most of the time we have seen that there are galvanic anodes jacketing that is being used to repair those. So repairing those areas just with pouring a grout is not really a solution. It's always better to have the galvanic protection or the impressed current cathodic protection for those. And I've been involved in many projects where we do distributed anode systems, the long anodes that are being installed around that area, submerged areas and the tidal areas. So the condition assessment is done on the low tide, medium tide, and high tide level. And based on that, the anodes are tied, connected to the steel, and then they are encapsulated with a mortar, specialized mortar for that. So this is galvanic protection should be done. But as far as how they are being evaluations, there are many ways of non-destructive testing, semi-destructive testing, all those tests which are available and in the market, you know, they are acceptable. Hope I answered the question.
Thanks, Amit. Another question from Matthew Mazzoni. Can you comment on the importance of electrically isolating the repair material from the original material?
Well, I mean, it's when you are, as I said, if you've seen the first animation that I've shown you on the incipient anode effect, if we are applying our repair mortar, which has an excellent chloride diffusion resistance property, that means we have addressed that part already in that specific zone. There is no problem in it, and that area is going to remain perfect in that zone. However, the adjacent areas, what my school of thought is that it's always good to have the anodes in the parameter in order to extend that the galvanic protection for that. How to separate it? Honestly, sometimes there are provisions of applying some coatings or silanes. Probably that would work. But my recommendation is always to use, in order to avoid the incipient anode effect, it's always good to have the anodes at the parameter at least, in order to avoid that incipient anode effect and the side effect for that. But normally the best way to repair is to have the similar properties of a repair mortars, compatible in terms of modulus of elasticity, tensile strength, compressive strength, and of course the shrinkage properties are very important in microstrain. As I said, most of them, they are around 500 to 656 days, 720 days in 7 days. So if we take care of all those things, that would provide a good durable repair mortar. Hope I answered the question.
That's it. Yeah, I guess part of to add to that, it really depends on what your objectives are with the repair. So if you've got good knowledge about the substrate material, let's say it is extremely highly resistive, you might choose to isolate the patch from that, or you might choose to use a highly resistive material and no anodes, but you need to consider the pros and cons of both, and hopefully have a discussion with your client if that's the space that you're working in.
There are some very high resistivity mortars available in the market, but I'm not sure whether they would still avoid the incipient anode effect. As far as in the new structures is concerned, it is really recommended to use a high resistivity mortars as in order to be at par with the high design life, high performance concrete. But this incipient anode effect is mainly, when I'm talking to incipient anode effect, is mainly for the old structures and the remediation phase. For the new concrete defects, yes, you very rightly said, Graham, high resistivity mortars should be used and preferred.
Okay, I've got a couple of other questions that maybe others might be afraid to ask, but I'll put them out there to you. With the use of anodes in a patch repair, is it Fosrock's technical position to still take 20 to 25 mil behind the bars, or are you comfortable with just exposing the bars, leaving them partially embedded, and allow the anode to do its job around the back?
That's a very good question, Graham. So if you can, for example, if you see that the steel reinforcement is corroded but the concrete behind it is very, very hard, but the corrosion is to an extent that steel is not flaking, really. Because corrosion control and corrosion protection or cathodic protection is one thing, and structural strengthening and repair is another thing. So it's structural repair, strengthening of a structure is not a replacement of corrosion protection, and corrosion protection is not a replacement of a structural repair. So if you, in case that the steel, you can still see the steel cross-sectional in more than 85%, but the concrete surrounding it is very tough, not possible to break at all. Then we can use the drill anode method for the corrosion control, as I said, as well as the patch repair as well. So there are different school of thoughts on that, but I personally believe that if the steel has lost more than 20 to 25% of its cross-sectional area, it has to be replaced or overlapped with the new steel. Have to go beyond and behind it and all that. But in areas where you can still apply anodes on case-to-case basis, again, we have to see what is the total chloride level at that area. But it's doable without really breaking and disturbing the whole structure if the steel is not really very bad.
Yep, good, thank you. What about in the perimeter of breakout? There's often a discussion comes up where, or there used to be, about undercutting the edges, so it's slightly dovetailed into the substrate. I think I know your answer, but I'm happy to take it again.
Well, I mean, it's normally we say that I used to have a very good slide on that. We normally don't specify or add that in our technical data sheet because, again, it depends on the site. You don't have to do it all the time, but a normal square and rectangular edges are good. There should not be acute angles at the corners. There should not be a zigzag pattern. So if we have a reasonable rectangular and square edged saw cut substrates, that's fine. I've seen even some people hack the edges as well, where they saw cut, to avoid any smooth surfaces. But once you have saw cut it properly, your inside geometry of the repair is good enough to hold and bond that product. But if you could if you could do it further, taper it in an angle for a good bonding, that is also fine. But honestly, it works both ways.
Yeah, I'm in that boat as well. Like if the bond isn't working, relying on a dovetail, that's crazy. The other thing about drying shrinkage and managing drying shrinkage, you know, if we've got 600 microstrain, that's 0.6 of a mil in a meter distributed across the surface. The side effects of, let's say, poor quality control on site, which might include layout of the repair configuration, such as excessively long repairs. Have you got a comment on, or some tips for the audience?
Yeah, so normally if you have long, narrow repairs and where the steel rebar is not exposed, so we always restrict it to a 20:1 thickness to depth ratio. 20 times the thickness of the repair is that we should go at one time. So if it's a long, narrow repair, so we can do always in alternative panels. You repair in one sections and then checkerboard method type of things, and they should not be carried in one go. So in our data sheet, we very clearly mention about 20:1 ratio, thickness to depth, minimum thickness to depth ratio. That should be considered definitely. What was your first part of the question, Graham?
I guess first part was the quality control on site.
Yeah.
You know.
Yeah. So for the drying shrinkage is definitely, as I said, that is an acceptable norm in the repair mortars. Is considered to be really good. But what is important is the saturated surface dry condition. There is a lot of debate about saying how could we achieve the SSD. And I always say that SSD is a very subjective term, but it is still a safe compromise. So normally if you can get 4 hours in total as an SSD, water sprinkling, specifically for the old structures, that would really improve the bond and would also anchor the other parts, which is the shrinkage and all the other factors that are involved. So it right away starts from, as I said, soldering and all the surface preparation, but the second part is the SSD, which is very important if you are not using epoxy bonding agent, for example. And then followed by the application, and then post-curing is very important. Specifically for microconcrete, curing is very important by either a curing compound or by a water curing. So these are the points which are good for the quality control. Some applicators I've seen, they use the polythene sheet taped around it tightly around the repair area after applying a curing compound even. And I've seen some companies are using such method for the last 20 years and they never had a single crack in their repaired areas. So what they do the same thing, saw cut and SSD and application curing with curing compound and then tightly taped with polythene sheet. Perfect. You know, no need to come and apply water and all that stuff again and again. So it works very well.
Yeah, good stuff. Well, we are getting close to time. There's a little bit of wrap up to do with future ACRA things, but I guess a little virtual round of applause for you, Hamid. Thank you for putting that together.
Thank you very much for your questions, everyone.
Yeah, I think we've done all the questions, but if there are last minute ones, please pop them up while I'm talking.
You can always send it to Nicole, ACRA, and we could always address those questions.
Yes, there's Nick's back. Okay, so I will just close out the seminar. And again, thanks for everybody for logging in.